Solubility-Product Constant. So when an ionic compound dissolves in water or some other substance, that is an equilibrium process. There's things dissolving, but also things recrystallizing. So the solubility-product constant is an equilibrium constant for the equilibrium equation that describes the dissolving of the ionic compound. So we call this KSP, SP standing for solubility product. Again, reminder, we leave solids out of the equations, and a large KSP would mean that the compound's very soluble, you get a lot of ions, and a small KSP means it's not very soluble. So we learn those solubility rules, and we say, well, these things are soluble, these things are not soluble. Actually, there's not a real distinct line. It's not an either-or thing. There's a continuum, like so many things. And so the KSP tells us, is this really soluble? Is it a little bit soluble? So writing expressions for KSP, the first thing we have to do is write the equation for the chemical reaction. And we're going to write it so that we show the solid compound in equilibrium with its dissolved aqueous ions. So for barium sulfate, we're going to have barium sulfate solid as a reactant. And then over here, we're going to put what it'll form when it dissolves in water. So it'll form one barium ion and one sulfate ion for every formula unit of this that dissolves. These are dissolved, they're aqueous, and so their concentrations can change. This is a solid, its concentration can't change. So KSP equals the concentration of barium ion times the concentration of sulfate ion. And the concentration of the solid doesn't come into it at all. KSP values are measured, and you can look them up. Here's a table from your textbook, and we see that a lot of these are pretty small. Copper sulfide, 10 to the minus 36. So in the solubility rules, that's listed as insoluble. In truth, nothing is completely insoluble. Because if one formula unit separates into ions, then something has dissolved, and you could calculate a KSP for it. So let's write expressions for each of these. I'm running out of time, so I'm just going to do B because it's more interesting. So if we're writing a KSP expression, we're starting with the compound given as a solid, and then we're going to write the ions that it forms on the right side of the arrow. So this forms calcium ions. Those are aqueous. And what's the other ion? Hydroxide. Also aqueous. This equation has to be balanced. So you can just write the ions and then balance it, or you can think about it as you write it out and say, well, there's 2 hydroxide ions, there must be a 2 here. So that's the first step, writing the balanced chemical equation. And then the solubility-product constant expression is going to be, you can use the same, you don't have to memorize a separate thing for this. It's the products over the reactants, and we leave solids and liquids out of it. So the products over the reactant, but the reactants is solid, so we leave it out. So we're going to have calcium ion concentration, and we're going to have hydroxide ion concentration, and that's going to be squared. Any questions? So we can use KSP to determine what's known as the molar solubility. Molar solubility means how many moles of that compound will dissolve in 1 liter of solvent. We can calculate this from the KSP. It's usually abbreviated with a capital S. So if we want to do this one, we want to look at silver chloride. Now we learned that silver chloride is insoluble. If you look at its KSP, it's quite small, but a little bit will dissolve. And we can figure out how much. So what we need to do is we need to write the expression for KSP based on this balanced chemical equation. So KSP equals the silver ion concentration times the chloride ion concentration. And we have a value for that. It's 1.77 times 10 to the minus 10. So molar solubility, S, is going to equal how many moles per liter of silver chloride will dissolve. So we look at this and we're like, we can't do that because we have two variables, right? Well, let's think about it. We're starting with just solid AgCl and no silver ion and no chloride ion. So if 1 mole of silver chloride dissolves, I'm going to get 1 mole of silver ion and 1 mole of chloride ion. The silver and the chloride ion concentrations have to be equal because they came from a solid in which they were paired up equally. If you took a truckload of shoes, brand new shoes from the shoe store, you would have an equal number of left shoes and right shoes because they come in pairs. So for every one of these that dissolves, I get one of those and one of those. S is the amount of this that dissolves per liter. So I'm going to say that this is equal to S and that's equal to S. Because every mole of this that dissolves gives me one of each of these. So I end up with S times S, which is the same as S squared, being equal to that KSP value. And then to solve that and find the molar solubility, I have to do the square root of that number. So 1.77 times 10 to the minus 10. No, try that again. 1.77 times 10 to the minus 10. Okay, I'm having trouble with my stupid calculator. There we go. No. Can somebody do that for me? Yeah. My phone is not cooperating. Point 0.000133. Okay. So that would be the molar solubility. That means that a very, very tiny amount of a mole, part of a mole, would dissolve in 1 liter of solution.